so astronomy in South Africa has a long history. It doesn't, of course, begin with the start of colonial times. There were the pre-colonial people in South Africa knew about the stars. They looked up. They had names for the constellations, names for the stars. They had mythologies associated with those. And in the early days of colonial times, there were visitors to the Cape who occasionally set up temporary observatories and made measurements of the stars. But the formal history of astronomy, or the permanent astronomy in South Africa, started with the British Admiralty, who had this problem with ships getting wrecked on the Cape Coast. And one of the problems, one of the causes of that was inadequate knowledge of the southern stars and inadequate timekeeping. So in 1820, they established a permanent observatory just outside Cape Town, in what is now the suburb of Observatory. And the purpose of that was to accurately locate stars in the southern hemisphere for the purpose of navigation. So an observatory was built. This is a picture. This is in fact one of the first photographs ever taken in South Africa. I think this is in 1843. This is what the main building of the observatory looked like then. And this is a picture of it as it is today. You can see the little domes on the roof have changed, but the building's pretty much the same. The major change, I think, is in lawnmower technology, which has come on somewhat. And then as the city grew, it became more and more infeasible to do scientific work from the cities. There was a lot of light pollution. And in 1972, the Royal Observatory in the Cape and the Republic Observatory in Johannesburg merged, forming the South African Astronomical Observatory. The headquarters stayed in Cape Town, but the observing field station was moved to Sutherland, and the big telescopes from Joburg and Cape Town were moved to Sutherland. This is a picture as it was in 1974, when there were just 4 telescopes up on the hill. And this is a picture as it looks now. So there are now 21 telescopes up on the plateau and various other scientific instruments, and there are more to come. If you look in the middle of this picture, right at the back, it's kind of looking small because it's a long way away. It's right on the far side of the plateau. This is another picture of it. This is the Southern African Large Telescope, which kind of dominates the scene. It's very much the flagship telescope of the SAO. And it's a little over 10 meters across. The mirror is a little over 10 meters across, which makes it one of the world's largest optical telescopes. And it's a beautiful machine. It really is. It's an amazing thing. It's also it's a very complex machine, and as such, it needs a large team of astronomers and operators and electrical and mechanical technicians, and of course software engineers to keep it running. I'm not here to talk about SALT, though. I'm going to talk about the so-called small telescopes. Now, they're small in comparison to SALT, but they are still very good scientific instruments. They may be old, but the optics are still good optics. And Sutherland is still a very good site, so we shouldn't be neglecting these telescopes. This is a picture of the 1.9 meter telescope at Sutherland. 1.9 meter refers to the diameter of the primary mirror, which is at the bottom, that round thing there. That's about 1.9 meters across. And I don't know if people may not be aware that you don't look through modern scientific telescopes. You have an instrument attached to them which collects the light and sends it to a computer, which you then analyze. On the left, I don't know if you can really see the nameplate of this telescope, but there it is in more detail. That date, 1938, is the date the mirror was cast for this telescope. So it really is, 76 years. It's an old telescope. And so we need to find ways to bring these telescopes into the modern age. So what do we do to keep them useful? The first thing, of course, mechanical things break down. The dome drive, the right ascension and declination drive to point the telescope. These kinds of things fail and need to be replaced or at least repaired. And then the other thing we need to do is we need to build instruments which are up to date and suitable for modern astronomy. And then that means we need to write software for these too. And once we've collected the data, we also need to streamline the data analysis and the data reduction pipelines. So what do we need our instruments to be able to do? What should they be? First thing, of course, they need to work correctly, and we need to be able to verify that they're working correctly. They shouldn't break down at the drop of a hat. They should keep on working. And they should be easy to use, easy for astronomers to operate, and they should support multiple modes of access. I'll talk a little bit about that in a while. They should be easy to develop software for, and they should be easy to maintain, and they should not be something which are out of date in 5 years' time. They should keep on going for, we hope, 20, 25 years still. The other thing is, Sutherland it's quite a long way from Cape Town. It's around about 400 kilometers away. Often observers don't want to spend a whole week there. They might want to just have one event which they want to look at, and it maybe takes an hour or two, and then they're done. Why should somebody need to travel all the way to Sutherland just for that? So we'd like these instruments and telescopes, if possible, to be remotely accessible. And in the future, we'd like to be able to run these things robotically. That means write a script which operates the telescope perhaps in the middle of the night, wakes it up at 12 o'clock, takes your data and switches off. So to facilitate this, we've been developing a software framework. What the framework needs to do is we've got lots of, an instrument is not one thing, it's not one piece of hardware, it's often several pieces joined together. So we need to support many types of hardware, and often these different components are, the most appropriate software for them is, it's not the same thing in each case. So we need to support multiple languages. They're not always in the same place, they're not necessarily always run by the same host PC, so it needs to be a distributed system, and we need to, as the instruments mature and as we think of new things to do, we need to be able to add new components. So to the framework we've come up with, we've separated each component of the instrument into 3 layers. There's at the bottom there's the hardware driver layer. Above that is a controller layer, and on top of that is a user interface. So each layer's implementation can be chopped and changed without needing to change the layers above or below. And then these various components, particularly the hardware and the control layers, communicate with one another using TCP/IP. So in this framework, the driver part of the instrument acts as a server with the controller component or the controller layer connecting to this and acting as a client. And we've mediated the client-server interactions using Apache Thrift, which I'll talk about in a little while. And then above the controller, we have a top-level controller which instantiates each of the controllers and provides some extra business logic. This is just a diagram of a particular instrument. You can see there are 3 hardware components. There's a filter wheel, a global positioning system, and a camera, each with their driver. So each of those 3 things are running in their own process. But each of the driver bits communicate through the Thrift interface with a dedicated controller, which, as you can see, is then marshaled by a top-level controller and the user interface that's on top of that. So the green at the top is one process, and then there are 3 processes at the bottom. We looked at a number of different ways of doing the communication, and we eventually chose Apache Thrift. What's nice about it is that it provides the interprocess communication layer and the remote procedure call layer. That does it for you, does it very easily. You specify a service in an interface definition language file. You then pass this ideal file through the Thrift compiler, which generates a whole lot of boilerplate code which makes everything work. And it also generates stub code for the client and the server. You can specify when you run the Thrift compiler which languages you want to generate code for, and it supports an enormous, every language you can imagine. Wherever possible, we use Python. Where we need to, we use C++. Here's a very simple example of a filter wheel service. There are three methods. There's an initialization, a move method, and a get status method. So the initialize, you just specify which wheel you want to initialize. The move, you say which wheel you want to move and the position you want to move it to. And then the get status method will return a dictionary of status for all the wheels. And you run that through the Swift compiler. This is just a very basic, I've stripped out a lot of stuff, but this is the kind of stub code that gets generated for the server side. For the filter wheel case, we have a programmable logic controller which actually drives the filter wheel, and so each of these methods would be replaced with something to send serial commands to the PLC. And then on the client side, there's a little bit more detail in the init method. You can see setting up the connection. And then if you look at each of the methods below, they're basically just calling the equivalent method on the far side. As I said, the user interface can be changed without needing any changes in the underlying controller. So we've developed many different, a number of different user interfaces. As we do our development, we normally have a command line interface, and that helps with diagnostics, testing the functionality of the component that we're building. One of the instruments we're building, an astronomer is developing the user interface. He's familiar with Python and Qt, so he's going to develop the first draft of that in PyQt. But for most of the instruments, we plan to have, we want them to be remotely operable, so we can have a web-based interface, and we've chosen to do this in Flask on top of Python, and Brian's going to talk a little bit about that in a while. Then, as I said, the last thing ultimately we'd like these telescopes and instruments to be robotically operable, so we're also developing a scriptable interface. To start with the instruments that we're applying this framework to, there's a big upgrade project at the observatory at the moment. The spectrograph on the 1.9 meter telescope is very old, the throughput is very low, so that's being changed. And while they're upgrading the hardware, we're also going to apply the new software framework. We're in the process of designing a new wide field camera, which will also go on the 1.9 meter telescope and will enable surveying of the sky at a much faster rate than typically with the narrow field cameras that we use. And then the workhorse instrument for several of the smaller telescopes at Sutherland is what's known as the Sutherland High-Speed Optical Camera, SHOC. There are in fact three of them, Shock and Horror, Shock and Disbelief, and Shock and Awe are their names. Shock and Horror is on my desk in Cape Town, but the other two are up in Sutherland and are used regularly. What SHOC is, it's a high-speed, very accurately timed imaging device. The camera is able to take images, take exposures every couple of milliseconds, depending on how you set up the detector, what your subframe and binning parameters are, but it can really take these images very rapidly, and it does this, it's triggered by, it takes these images in response to a trigger which is fired by a GPS unit. The GPS unit is, connects to the GPS satellites, which they have atomic clocks in them. They're extremely accurate. So the pulses which come down the line are accurate to the microsecond level. And then generally, to complete the instrument, one generally wants to have just a narrow band of light falling on the detector at a certain time. So we have one or two filter wheels above in the light path, which restrict the light to what the astronomer is interested in. This is a picture of the SHOC instrument. It's mounted on the bottom of, I think, the 1 meter telescope, which is sort of the yellow rim. You can see that's the bottom of the mirror. And the black box is part of the telescope. Then the blue box that you see it contains the filter wheel, so that filters the light passing through, and finally the light strikes the detector, which is at the top of the camera, right at the bottom of the instrument. You can see the black cable coming into the camera from kind of that crate up on the left. That's the control crate. There's a GPS unit in there, and the trigger signal comes down that black cable, and then the data passes up the white cable into a PCI card onto the host computer. when Shock was first put together, there were a couple of shortcomings with the interface. Well, in fact, the interface was 3 separate user interfaces on not even on the same screen. It made it quite difficult to use. There was a homegrown LabVIEW application which was developed in-house to control the filter wheels. The GPS manufacturer had an application, Windows only, to control the GPS, and likewise the camera had a Windows only proprietary application to control the camera. The problem with 3 separate user interfaces, if you had a workflow where you wanted to, say, do some work on the filter wheel, configure something there, then configure something on the camera, then make some timing changes, go back to the camera, you kind of had to move around from one to the other, and it was kind of clunky. So that wasn't great. But more importantly, when you save the data is saved in these files called FITS files, Flexible Image Transport System. And at the header of the FITS file is pertinent information about the observations you've made. Now, the camera, which is writing these FITS files, doesn't know about the filter wheel. It doesn't know about the timing parameters. So this kind of information wasn't being stored. It was expected of the astronomers to put this in by hand, but not all of them got that, and not all of them remembered to do it. And some of them spent a week at Sutherland taking data, went back and discovered that their data was worthless. So we'd like to get past that. So we've developed this new package. The first thing is it's a single user interface, one interface in a browser with multiple tabs. Secondly, the driver parts run on Linux, so we're freed from having to use Windows. The filter wheel driver component is written in Python using, as I said, we communicate with the PLC using serial commands, so we use PySerial extensively. Likewise, the GPS uses serial commands, so it's quite similar. And then the camera driver, the API that the hardware manufacturer provides is in C++, so we're obliged to use that. But using the framework, we can use all of these together. The great thing is that now we can use the top level controller that I mentioned to marshal all the information about the filter wheels and the timing and send that down to the camera, and so the camera, when it writes the FITS headers, it can include the information that we need. And in the future, we'll also be able to include telescope pointing information, right ascension and declination, and environmental information like wind speed, humidity, and then other things like the air mass and seeing conditions and so on. So I wanted to give an example of why one might need to do high-speed imaging using an instrument like Shock, what it's useful for. So this is an example. There are others, but this is an example of an occultation of a minor planet like Pluto. So the Earth is relatively close to the Sun in the solar system, so it whizzes around quite rapidly at about 20 kilometers a second. Pluto is so far out that from our perspective, it's almost stationary. So we kind of, we zip past it, and it seems to be in more or less the same place. And likewise, the fixed stars are so incredibly distant that they are, for all intents and purposes, stationary. Pluto is also far enough away that you can't, even with the best space telescopes, you can't resolve much more than a few pixels. You can't really see details of Pluto. And if you want to figure out more, occultations are one opportunity to do that. These kinds of things, an occultation is when something moves in front of something else and blocks the light from that distant star. So they don't happen often. As I said, Pluto is essentially a point source in the sky, and how often that happens that one point source moves in front of another. This kind of thing happens maybe a few times a decade. But when it does, well, you can aim an instrument like Shock at that and take a number of readings. So here's, this is very interesting. This is in fact an occultation of a star by both Charon, which is a moon of Pluto, and Pluto, a grazing occultation of Pluto itself. Now you can see as Charon moves in front of the star, there's a very dramatic drop-off of the light. It sort of goes from a high level down to almost zero. And then there's a very sharp rise again. But as it passes in front of Pluto, you can see it sort of, there's a rounded shoulder as it drops off, and a rounded shoulder as the light reaches maximum intensity again. And you can only really characterize that kind of rounded curve by taking many exposures a second. You know, if the Earth's traveling at about 20 kilometers per second, and Pluto's diameter is about 2,000 kilometers, means this kind of whole event happens in about 100 seconds. In fact, for Charon, even less, because it's got a smaller diameter. So you'd like to characterize this properly by taking many, 20 exposures a second to properly characterize that. Anyway, the upshot of this is you can see Charon has no atmosphere, but Pluto, that rounded curve, the interpretation is there's in fact an atmosphere on Pluto, and there's no way that you'd be able to tell this except by using this kind of, taking this kind of observation. Okay, so we don't only use Python in instrument building. There are a lot of other smaller projects that we use. One of the things is we want to characterize the detectors, the charge-coupled devices that we use in all our instruments. We want to generate what's known as the photon transfer curve, and it's quite easy in Python, both to automate obtaining the data for these things and then for these curves, and then you use Python to calculate the variance of each image, and you plot that against the exposure, the length of the exposure for each image, and you get this curve from which you can deduce data about each CCD. Has slightly different properties. You can deduce the properties of the CCD, and then you can use that when you use the instruments for scientific observations. Python is used extensively. Steve talked yesterday about Python in the SALT data reduction pipeline and also in the smaller telescope pipeline. It's used as a glue language to join many tools together. And the last thing is that I'll mention is we have an observatory-wide time service where we provide time accurately for many services at the university observatory. This was done using various equipment, I think, which was built in the 60s and coded in C, and we've now replaced that with a Raspberry Pi connected to a GPS system, and Python is the coding language for that. So Brian's now going to talk about the shock interface a little bit.
Thanks, Carl. Hi, everyone. So I'll be talking to you about the web interface that we've built for the shock instrument on top of this new controller layer that Carl just mentioned. I'll take you through some of the decisions that we've made along the line, and at the end, if there's some time, I'll show you a quick demo to show you how it all works. To start with, we had some overarching goals and requirements. First and most obvious one, I think, is that it needs to be remotely accessible. And since we're talking about a web interface, it should be accessible from a browser. It should also be fast and responsive. And the interface should be reliable. And since we're dealing with valuable scientific data, if it's running on the same system where the data is being processed, it shouldn't take up too much of the machine's resources. So here's a diagram showing you how the interface fits, or where it fits into the rest of the system. So the idea is for the astronomer to be able to drive the whole instrument from within a web browser. They'll open up their favorite browser on a laptop and start their observation. So in the diagram there, you can see the web browser connects to the web server using HTTP. And then the web server also acts as a Thrift client, so it can speak to the hardware on the other end. So that basically covers the how things are put together and how they communicate with each other. What did we use to build it and why? Starting with Python. Now, besides all the obvious technical reasons, I think one of the main reasons is that Python is already widely used at the observatory. So in theory, there's plenty of people that can contribute to the project if they want to. Choosing Flask honestly had a lot to do with the fact that I had used it before, and I kind of liked its minimal design. Compared to something like Django, for example, it's a bit more flexible in some ways. Django, I mean, a complete framework, a more complete framework, many decisions have been kind of made for you, so it's a bit harder to adapt if you have specific needs. And then display incoming data from the camera, we need a fast connection between the web browser and the web server. For that we use something called G-Unicorn, which is an HTTP server, and WebSockets. And then just lastly, for completeness sake, in the browser we use something called Backbone JS. And that wasn't part of the initial design, but I'll talk about that a bit later. And then finally we used a Bootstrap theme for the actual UI, which saved a lot of time because we didn't have to write a bunch of CSS. So just a quick overview of what Flask is and how it works, if anyone who doesn't know. It's a micro framework, which means it gives you the bare minimum to build a web application. And it combines two other projects to do that, something called Werkzeug, which is a whiskey toolkit that allows your application to speak HTTP. And then Jinja, which is a templating library. Very similar to Django's templates, if you've ever used that. So the basic idea behind Flask is that it routes URLs to code or functions. And I'll show you a quick example of what that means. This is a hello world example from the Flask website. All you need to do is import Flask, create a new Flask application, and then decorate the function and indicate which URL that function should handle. In this specific example, if someone visits the root of your site, they'll see the text hello world display in their browser. So I want to take the rest of the talk to just go into some of the technical aspects to show you how it's all put together. In the initial design, the web browser communicated with the web server using something called JSON RPC. And so what that means is it would send some encoded data to the server containing a method name and some parameters. And the server would then invoke that method and return a response to the browser. Now, JSON RPC is a fairly straightforward protocol. But one of the downsides is that you need to embed a lot of implementation details in your client code. Later we implemented the GPS functionality in the interface, and at this point the JavaScript was kind of starting to spiral out of control. So I was looking for a way to give it a bit more structure and make it more maintainable. And I'd used Backbone JS before and liked it for some of the same reasons I like Flask. It's lightweight and doesn't make too many assumptions about what you're building or how you're doing it. Now what the effect that that has is it simplifies the code on the client, but unfortunately it makes things a bit more difficult for us on the server, because now instead of asking the server to move the filter wheel to a specific position, we just send it the position we want it to be in. And the reason for that being is that one of the assumptions that Backbone JS makes is that your API endpoints needs to be follow a RESTful design. Okay, so to give you an idea of what the comparison between RPC and REST, RPC being a remote procedure call, REST is a representational state transfer. And on this side, on the REST, the new approach, we use a patch HTTP method because we only want to do partial updates. With the usual RESTful API design, post input is reserved for creating or updating resources. And it would expect all the attributes of the resource, even if they haven't changed. Now the tricky thing is that we need to somehow map this incoming data to methods that we want to invoke on the filter wheel controller. And for that, we create this kind of a proxy object or class. And then we define a property with a setter, and inside the setter, we invoke the method that we want to call. So if we set the position parameter on instances of the filter wheel, that will end up calling the move command on the filter wheel controller. So this is our patch handler. What we do inside the patch function is instantiate the filter wheel class, loop through each of the key value pairs in the dictionary that we receive from the browser, and then set each of those as properties on the filter wheel object. And to set all of that in motion, from the browser we call the save method on a backbone model, which ends up sending the patch request to the server. And in this example, it will move the filter wheel to position 8. And so that about covers the technical details. Now for the demo. The demo is just a series of screenshots, but I'll take you through the typical workflow of setting everything up and starting the camera for data acquisition. Okay, so there's the new Shock web interface, or the Shock interface rather, all nicely contained within one window. I'm not sure if you can see this, but on the top left we have a main menu with links to the various components of the instrument, the filter wheel, the GPS, and the camera. Now we only have one of the two wheels installed in the filter wheel on the right side in the B slot. At the top you'll see there's some green indicators there indicating whether the filter wheel has been initialized, whether it's centered or moving, and so forth. And then below that there's a control showing you what the current position is. Below that we have the required position with the move and initialize buttons just below that, and then a list of filters and a reset button. Now if you want to move the filter wheel to the empty slot in position 8, we'll change the required position to 8 and click the move button. This is just an updated view to show you what it looks like once I've moved it to position 8. We then jump to the camera interface, and unlike the other components, the camera isn't always running because it's got a cooler that shouldn't be running for extended periods. So we switch that on, and that brings all up all of the controls for the camera, and it'll start cooling to a point where that will reduce the amount of noise in our data. Okay, and then we go to the GPS, so we can configure how often the camera is triggered. We set the start date and start time to some point in the future that we want to start our observation on. We click the apply button to save our settings. Now we go back to the camera, and it's by this time it's kind of cooled down to a stable point. You'll see the green indicator at the top there. We configure some of the other parameters, and we click the start button. And that will bring up a live view of the data as it's coming in from the camera. And that just about wraps up the demo. I'll just hand it over to Carl for some closing thoughts.
Thanks. So, as Brian showed you, we have a web interface now to the software. One of the things I said about Sutherland is it's a long way away. It's also, in winter, it's pretty cold. And when you sit in the domes taking data, the domes are not necessarily the warmest places. You sit in what's known as the warm room, but in fact that's a bit of a misnomer. It's the same temperature as the rest of the dome. And This is after a particularly bad blizzard when the snow actually got in through the dome cover, and you can imagine what it's like. So now that we have a web and remote interface, we're hoping that you can take your data somewhat like that, rather. So,
Cool.
thank you.
Thank you, Carl and Brian. We have time for a couple of questions, but for questions, I'm not sure how many people know that despite everything Carl and Brian have said about not wanting to go there, it is actually a really nice place to go and visit if you don't have to. And and they do have, do they still have the tours?
Absolutely. It really is a nice place to go. I don't want to knock it. And they do tours. It's especially to take a tour and to see the telescopes and to see SALT. It's an experience everybody should try at least once.
Cool. Go in summer. There was a question over here. If someone can just pass the microphone back a bit.
Do the scientists ever allow anyone to sort of shoulder surf?
Sorry, I didn't hear.
Do the scientists ever allow anyone to shoulder surf? Now that you're streaming the data out?
No. I mean, the data is, it's published eventually, but I think the raw data isn't generally available as far as I know. Yeah.
Any reason why not? I mean, it sounds like...
I'm not really sure why it would be. You know, I think, sure, if somebody really wanted to see the data, I think that it would be available, but it's not published generally for everyone to see. The other thing I didn't mention is we have this web interface. We haven't implemented it yet, but we're going to have to be concerned about security. We don't want multiple people to be accessing the instrument at the same time, and in fact, we don't want anybody who shouldn't be, so we're going to have some authorization and authentication mechanism built in, which we haven't done yet, but that is part of what we're going to do. At the moment, it runs on a private network, so it's all right. But sure. But in terms of the data, if there's something you particularly want to find out and write to the astronomer or contact someone, it would be available, I think.
Cool.
So you mentioned this time service for the observatory, which
Yes.
obviously has some hard real-time requirements. Is Python actually sitting in a hard real-time path, or is it just controlling some real-time systems?
It's controlling real-time systems. So the time comes from a GPS unit, which is connected to the Raspberry Pi. As I said, the previous system was a bunch of components, largely written in C a long time ago, and they get they get the time from a GPS system. There's a backup system where they, I think they use the 6 pips from the SABC. There's a number of ways of getting the time, but it is primarily GPS based, and so the Python is acting as a kind of a glue for all of that. Yes.
Cool. I think we have time for one more question. Can you wait for the mic? Thanks.
Can you just tell us why you chose Apache Thrift and what your other options were?
Initially I looked at JSON RPC as the RPC layer. We looked at a couple of things for the inter-process communication layer. I looked at vanilla TCP/IP. We looked at 0MQ was one of them, and JSON RPC I think had the drawback. It wasn't a single provider of. So there was somebody did JSON RPC for Python, somebody else did JSON RPC for C, somebody else for C++, and I don't know. I didn't find it work together very nicely. I think the C one was not very complete, or didn't work very nicely. Thrift just works, and it's one. It was originally produced by Facebook and then put into the Apache incubator, and it just works. It generates. It does both the IPC and the RPC, which is great. What else did I look at? I looked at 0RPC based on top of 0MQ. That unfortunately only supports Python and Node.js, which no good for us. Yeah, so we ended up with Thrift, and the documentation of Apache Thrift is not fantastic, but once you've got it working, it's great.
Cool. Thank you once again.